Almost there. Everything's just rebelling today.
Technology.
Yeah. All right. We'll do what we can. All right. Oh, there it is. Perfect. All right. Good deal. All right. So, Wayne, we got you live. Hi, everybody. Sorry for the technical difficulties. Let's see. We're only 15 minutes late. My apologies. Microphone technology, right? So welcome everybody to this month's member meeting for BSAS. We're going to go ahead and start off with our special guest speaker, Dr. Wayne Keith from McMurray University in Abilene, Texas. You never know where you're going to meet people. I oddly met him in a fan group of bunch of dads of a blue dog from Australia. So again, you never know where you're going to meet people, but he talks a little. He mentioned on there that he works with the magnetosphere, and it seemed pretty interesting for us. And so I asked him if he'd be willing to do some outreach for us, and he jumped at it. So without further ado, we'll give Wayne the floor. Before we start off rambling on our own, it's a pretty neat picture there, Wayne, on your backdrop. That's not from
thanks.
just recently, was it?
No. This is just some stock photo that from a long time ago.
Nice. Yeah, we can send you one now.
I know, right? I should update it with one because it's in fact that bandits group that we met on, that was just inundated with pictures that night.
Yeah.
I think that's the first place I saw it was people posted on that group page, and some of the pictures were amazing.
Yeah,
and
no doubt.
You know,
all right, well, we'll go ahead and give you the floor. Thank you.
Sure. So I said I'm going to be talking about the Earth's magnetosphere. I like to call it Earth's invisible shield because it sounds cool. This is my, for anybody talk. So it won't be super technical, but if you guys have questions, we can go into the weeds, if you want to. Let's see if I can make this work. There we go. So I grew up in Stephenville, Texas. I don't know if you guys have ever heard of it. Has a local university there called Tarleton State, where I got my undergraduate, and then MSN and PhD from Rice in Houston, which hopefully you have heard of. And then I was worked part of my grad student years and also postdoc at a place called Southwest Research Institute in San Antonio, and that's where I got to take my trips to Sweden and get to see the aurora for real. So that was really cool. And then I spent 2 years at NASA Goddard Space Flight Center as a research associate. So I wasn't like a national NASA employee, but I was actually paid by the NSF. And then I spent a year at Angelo State, and then since 06, I've been at McMurray University in Abilene, which is only about an hour and 45 minutes from Stephenville, where I grew up. So I ended up fairly close to where I started. Okay, so obviously the Earth's magnetic field is not something that we can see with our eyes. I mean, obviously with the effects, like the aurora, we'll talk about that later. But you look up the night sky, of course, you're not seeing, the Earth's magnetic field around us, but it's actually really important. And there's a reason why I call it Earth's invisible shield, because without it, and we'll look at other examples of what can happen without a magnetic field that protects us from the solar wind and from high energy cosmic rays. And without one, it would be bad. In fact, I'll talk later about specifically Venus and Mars and how the lack of a global magnetic field has most likely contributed to their inhospitality for life. I just want to quickly plug. I did write a book, and this is not just a stock picture on this book cover. We've contacted a guy. I want to say he lives in Hawaii, although I don't remember where he was when he took this picture. I think maybe in Alaska. And this was actually during an event that we talk about in the book, Magnetospheric Substorm. And so we contacted the guy who took the picture, and we're able to get the rights to the picture in exchange for, I think, $200 and a copy of the book. So look at the barter system there. And my co-author, Walter Heikla, he negotiated all of that. He actually wrote the first edition of this book, and I just helped a little bit. And then when he was going to write the second edition, he invited me to be the first author, which was really amazing. because I hadn't seen him in a long time. He was actually my advisor's advisor. And so when I was a grad student in San Antonio, he would come down from Dallas. He was at UT Dallas and visit his former student, uh, David Winningham, and who was my advisor. And so I call him my grand advisor. And so it was really fun to get to write a book with him. He's, I think, 97 now, still living in Dallas. And so it was a pretty amazing experience. This came out in 2021. So I was writing it during all the COVID funness. And I thought second edition, it won't be that bad. Yeah. Don't ever agree to something like that unless you know what you're getting yourself into. All right, so I'm going to basically talk about this in three different stages. We'll start out with the history of our understanding of the Sphere. Obviously, it's been there, since prehistory, but our understanding of it has evolved over time. And then I'll talk about the different parts and regions within the Earth's magnetic field, and then applications in science and how it affects life on Earth, and how do we study it. So obviously, some aspects and some knowledge of it goes back a long ways. Ancient people knew about the auroras. They didn't necessarily knew what was going on scientifically, but they knew that they were there, and that was some effect. And of course, just as a disclaimer, this is a very, very quick, high level version of events. But this, like I said, this is my public lecture, so I try to keep it fairly brief. I like to start with a little, pre-scientific history. So this is a Lap legend. Lapland, of course, is northern Scandinavia. So when I was in Kiruna, Sweden, working on a spacecraft instrument, we were in Lapland. And so I learned that, according to ancient legend, the Arctic fox is who created the aurora by switching its tail. And I got this, actually was in the first edition of the book, so I didn't write this. It was my co-author wrote this. There's a idea that there's actually an element of truth in this old ancient legend, because switching the tail will create an electric field, which is a part of the process. And so it's kind of a stretch, but it's a very tiny grain of truth and all that. And then going into the 1600s, we have William Gilbert published his book stating that the Earth was a giant bar magnet. And that, of course, was evident from the way the compasses would have been understood to work in those days. We now know that it's not like a permanent magnet. It's being generated by convection of the iron nickel core. So it creates a dipolar field that's similar to a bar magnet, but it's actually being actively generated by flowing charged particles, which is how you create a magnetic field. So you need a liquid conducting layer, and you need differential rotation in order to be able to get that to generate a field. Now, also at about the same time, we have Johann Kepler, who was looking at comets. Of course, it was a little bit later that Halley figured out that comets were, returned. But at that time, they knew about comets. They just thought they were one-off events, and they could see the two tails, the really bright ones. And Kepler correctly guessed that the dust tail, the one that looks more white in this picture, was caused by dusty material that would sort of drift behind the comet on its orbital path due to sunlight, which is basically the correct answer. But they didn't know what the other tail was. It points directly away from the sun. And it wasn't until the 20th century, the early 20th century, 1940s and 50s, they started figuring out that there was a rapid flow of ionized particles called the solar wind. And that what you're seeing is the more bluish, straighter tail is individual atoms that were becoming ionized and charged and being picked up by the magnetic field of the solar wind and carried away by the solar wind flow. So in a way, comets were really the first spacecraft that we used to really study interplanetary space. In fact, up until basically the days of Sputnik and the early space race, comets were being studied to try to better understand the environment in interplanetary space. And then we have Christian Birkeland, who's not real well known in the United States, but certainly very, very well known in Sweden, which is where he was from. And he studied the aurora, and he's the first one who predicted in 1913 that there was a solar wind. So this predates most of the looking at the comets. I maybe should push those slides around. Oh well. And so he actually used, you can see here, he was an experimentalist. And so he used a magnetized ball to represent the Earth called the Terrella. And he would introduce a plasma into this vacuum chamber and see that it would flow along the magnetic fields and create a ring around the poles of the ball. And so he's really the first person to figure out that the aurora is charged particles flowing along magnetic field lines and going down to interact with the Earth's surface or the Earth's atmosphere, really. So, so that was pretty important, early magnetospheric physicist. I don't think that word had been coined yet, but he's certainly given credit. And then we have Carl Stormer, who basically went a step further from Birkeland and showed mathematically, and this is the kind of math that I would do in like a social physics class, but I'm not going to do all that here. That if you have a charged particle in a dipolar field, that it would become trapped and it would sort of create a magnetic bottle. And that's because where the field is closer to the Earth is stronger, and where the field is farther from the Earth is weaker. And so, as you can see, these sort of squiggly lines on the slide here, when they get close, when the particle, so the first type, it's three types of motion that the particle's undergoing. The first is it's just spinning in a circle around the magnetic field line. And so it's just, it's called cyclotron motion. So it's just going around a circle around the field line. And if the field lines were perfectly straight, it would just go like a spiral forever and it would never change its direction. But as it gets a stronger and stronger field, then less and less of its energy is towards motion along the field, and more of its energy is spinning about the field, and so it slows down, and eventually comes to what we call the mirror point, which if that's above the atmosphere, it would never interact with the atmosphere. It would stop and reverse direction, and then go back to the other pole and bounce. And so that's the second type of motion is called bounce motion. So you have the cyclotron motion around the field, you have the bounce motion between the poles, and then the fact that this field line is curving actually requires a force into or out of the screen. And so that causes the entire thing to drift around the poles. And you can see from the two arrows going around the Earth that the electrons and the protons drift in opposite directions because they have opposite charges. So those are usually referred to as the three magnetic invariants of trapped particles in a magnetic field. And by the way, if you read something about those tokamaks and places where they try to contain super hot plasma in order to study nuclear fusion, it's basically the same idea. You're having this super hot plasma and you're trapping it magnetically. In the case of a tokamak, it's basically a toroid. So just imagine instead of having the two ends go down to the Earth, you just connect and you would have just a circle, and it would just spiral around in the circle forever. And so basically, you just connect the two ends of the bottle, so you don't ever have to worry about any leakage. In this case, of course, any leakage would actually interact with the Earth's atmosphere and would excite the atoms and cause aurora and that sort of thing. Okay, so our modern concept of the Earth's magnetic field forming this sort of magnetic bubble, if you will, that separates the near Earth environment of magnetic fields and plasmas from the solar wind coming from the sun. That actually goes back to Chapman and Ferraro, a very important paper that they wrote in 1931 that still gets referenced pretty regularly. And they correctly predicted that most of the solar wind flow would get deflected by the magnetic field, and it would form a cavity. And so the Earth's magnetic field would be separated from the solar wind's magnetic field as it flowed by. And then we have the Explorer 1 spacecraft. So that was the first spacecraft that the U.S. put into orbit as our answer to Sputnik. Unlike Sputnik, which only would beep beep with the radio, they actually put some scientific instruments on Explorer 1, and one of the instruments was a Geiger counter that James Van Allen put on there, and because they didn't really know what the radiation environment would be out in space, they weren't really sure what to expect. But at two different altitudes, the Geiger counter completely saturates, meaning that it just pegged out the needle. It pegged out and couldn't read anymore. And that was surprising. And so they, of course, sent follow-on Geiger counters with higher limits, and were able to get readings, and were able to figure out that it was this magnetic bottle effect. It was trapping these ions and electrons, mostly protons and electrons, in these two regions that, of course, today are known as the Van Allen radiation belts. But that's how they were discovered, basically accidentally. I mean, we knew that there would be some radiation in space, and that's why we put a Geiger counter. But they didn't understand the details until after they'd sent a few missions through it, and sort of figured things out. And of course, in more recent times, we have even more sophisticated ways to see the interaction between the Earth and this plasma environment. And so in this picture, this is the image spacecraft, and it's well named. Of course, with NASA missions, they always want both the acronym to mean something and to say something that's related. And I can't tell you exactly what the letters stand for in image, but it was the first spacecraft to really be able to take images of the sort of innermost plasma environment around the Earth. So here in this picture, you can see the white circle that's drawn on. That is where the Earth's surface would be. And so you can see on the left side, there's labeled air glow. So that is just sunlight hitting the daytime atmosphere. And then we have the circle of the aurora. Notice it is off center because, of course, the magnetic pole is off center from the geographic pole. But the way they did this picture is actually really clever, because the particles that are interacting like this are charged particles, and therefore they're going to stay locked onto those magnetic fields, and they're not just going to fly in a straight line for you to create an image from them. But what they figured out was a certain percentage of them would become neutral. That is, a proton electron would combine and become a neutral hydrogen atom and just start zooming off in a straight line. And so they figured out that if you were imaging the right area from the right vantage point, there was enough of these particles that would become neutral and then travel in a straight line that you could actually create an image from that. And so that's how they were able to do this, and that's why it only works really close to the Earth, because other parts of the magnetic field, the Earth's magnetic field, that goes many Earth radii out, like 10 Earth radii out on the day side, it's just not enough of those particles to generate a picture from. So it was really, really clever instrument. This is actually one that was in the news fairly recently, because the spacecraft died, and then an amateur radio guy heard it making beeps, and there was briefly some hope that they could actually contact it and revive it, but that didn't work out. So it's still orbiting, but it's dead in place, like a lot of other things. Okay, so now we're going to quickly go through some of the different regions and describe some of the different regions in a little bit more detail, and then sort of put the whole thing together at the end. And so first of all, starting from the incoming solar wind, the first thing the solar wind would encounter is the bow shock, which is a shock wave, a supersonic shock wave. And of course, one thing that surprises people is, how can you have things be supersonic in space when there's no sound in space, right? That's what we all grew up learning, and that's kind of true. I mean, obviously, you don't have enough particles. The density of the solar wind is like 5 atoms per cubic centimeter, so it's way too dense to have any sort of collisions between particles create a sonic wave. But it's magnetized, and what's interesting about a magnetized plasma is the individual particles, they can move freely along the field lines, but they can't really move freely across field lines. And so if you see here my little animated GIF at the bottom with a longitudinal wave, this is, of course, showing how it would work with particles, where the particles wiggle back and forth. It creates, compressions and rarefactions like you have with regular sound waves. But now imagine that those are magnetic field lines. And so remember, the distance between field lines indicates their strength, which is why if you look at the picture, you look at the picture of the Earth, the field lines are closer together near the Earth where the strength field is stronger, and they get farther apart as they go away from the Earth when the field line is weaker. And so if you have two magnetic field lines and you try to squish them together, that creates a stronger field, which wants to equalize itself back out. And so if you push on the field, it's going to push on the next field line and push on the next field line. And that is called a magnetoacoustic wave because it basically looks like a regular sound wave, but it's the magnetic field that's causing the propagation. It makes the plasma act as if it was collisional. So even though the individual particles aren't hitting each other, the magnetic field means when one moves, the next one moves, as if they were colliding. And so you can actually refer to a magnetosonic wave and a speed of sound that is a speed of propagation of those magnetosonic waves in a magnetized plasma, which is pretty cool because it means that you can just use the regular physics that you would use studying supersonic flow on the Earth to study the solar wind's interaction with the magnetic field. In fact, both when I took it as a grad student and when I teach it to my undergrads, we start out with an airplane flying through the air at supersonic speed because all the physics is the same. And so once you sort of establish the physics for a supersonic airplane, say, oh, and by the way, the exact same physics works for the solar wind hitting the Earth's magnetic field. Except in that case, of course, it's more like a rock in a stream because we're the stationary one and the solar wind is moving past us. Now, I guess you could think about it as a supersonic wind tunnel. And so the purpose of the bow shock, both in the solar wind and with just a regular shock wave of a supersonic airplane, is to allow the material, the solar wind particles or the air, to be able to get out of the way because normally the way information is transmitted like through the air is by sound waves. Well, if your object is moving faster than the speed of sound, then the air doesn't know to get out of the way. And so the way physics fixes that problem is by having this bow shock. And so after the air or the plasma goes through the bow shock, it gets heated and compressed so that now it's subsonic relative to the object. And so you can see in this picture, up until the solar wind hits the bow shock, they're straight lines. They have no idea the Earth is there, right? But then once they go through the bow shock, then now they've been heated and compressed, and they're subsonic relative to the Earth's magnetic field, and they're able to flow around it, as you can see with the flow lines starting to bend as you go through the bow shock. And then the plasma that's in between the bow shock and what we call the magnetopause, so the entrance into the Earth's magnetic field, is called the magnetosheath. As you can see here, it sort of covers around the outer most part of the Earth's magnetic field. And that's where this heated, decelerated, newly subsonic relative to the Earth solar wind is. And most of the sun's flow from the solar wind, it goes around through the magnetosheath and never actually penetrates into the Earth's magnetic field. But of course, some of it does. And so, as I mentioned, the boundary between the magnetosheath, the subsonic flow of solar wind, and the region dominated by the Earth's geomagnetic field is called the magnetopause. And of course, anytime you see, pause in science, it usually means the edge of, right, or the end of. Oh, I'm getting a message. My internet connection is not good. You guys still read me okay?
Yeah.
Okay, I'll just checking. So this is pretty much the earliest clear identification of a spacecraft transitioning from the fast, steady supersonic flow in the let's see. No, this is the magnetosheath to the magnetopause. So it's still relatively fast and steady, but it's subsonic. relative to the Earth. And so you can see in the up until about the 8 RE or a little before 18 UT on the top, that the little dots are pretty steady, right? And then right there at about 8 RE, a little bit past that, you see the field line changes direction, right? Because the different components, the solid and open dots are different components, like X versus Y of the magnetic field. You see the component switching places, so it means it's a change in direction, and it gets a lot more chaotic and uneven. And so that is a transition, one of the first ever clear transition um, from the magnetopause from the Earth's magnetic field to the magnetic sheath. All right, so another place that we have a lot of plasma getting in is called the cusps. And if anytime you see a picture of the Earth's magnetic field, you have those dipole lines, right? Well, some of them close on the day side, some of them are swept back in the night side, and so there's this sort of funnel shape that's the transition from the day side to the night side field lines, and that is a region of weak field. Remember, the distance between the magnetic field lines determines, or it's is a representation of, doesn't determine, but it's a representation of the strength of the magnetic field in that region. So we have this sort of funnel shaped weak magnetic field region, and so you end up with a lot of flow uh, of magnetic plasma being able to kind of go down in that funnel and getting down to low altitudes and getting into the Earth's region of domination inside the magnetic field. Um, and you can see this is actually a figure from a paper I did a long time ago, and you can see the couple of the cluster spacecraft, cluster one and cluster three, cutting through there. And so we're trying to figure out what regions they're passing through by looking at the squiggles on their plasma detector instruments. And then one of the things that I also worked on a lot when I was at NASA is comparing what the cluster sees at relatively high altitudes to what very low altitude spacecraft is. A series of spacecraft by the Air Force called Defense Meteorological Satellite Program (DMSP), and they mostly have cameras and stuff to look down at the Earth, but they also have some instruments that look up, and one of them is a plasma instrument that any plasma that's raining down along the field lines, it would see those. And so I would compare at the two different altitudes the plasma coming in. And in fact, the very first determination of the particle signature of the magnetospheric cusps from satellites was a paper by Heckel and Winningham, which was my advisor and his advisor, who was my co-author. And so you could say I'm really basically only a second generation person studying this because the people who literally discovered it were my mentors. So that's pretty cool. All right, so there's also, of course, ways for magnetic field lines to interconnect and reconfigure themselves. One thing to keep in mind is that magnetic field lines are not real objects. We talk about them bending and stretching and snapping, but it's really all analogy because it's really just a way to map the strength and direction of a magnetic field at any given place at any given time. And so magnetic field lines themselves are not physical objects. And so it makes it a little bit weird when you start talking about, things reconnecting and interconnecting and changing. It's really just a change of configuration of sort of, where if you followed, where the forces would lead you, it would just start taking you in a different direction than what it used to. So there's a little bit of confusion when it comes to that sort of thing. But this obviously, if you reconfigure, where if you follow that field line, it would go. Where if you reconfigure where that field line is going, then you can have plasma that's along that field line suddenly be going in a new place. And so if you have, we're showing here the interplanetary magnetic field in yellow, the Earth's geomagnetic field in red. And so if you get this interconnection so that suddenly a particle going this way just wants to go onto the red, then you can get a certain amount of plasma being sort of dumped into the geomagnetic field in that way. And this is really, I mean, obviously the actual physics of it is very complicated. and we're not going to even pretend to talk about that. But that is a process by which plasma can get into the Earth's magnetic field. So we've already kind of talked about its discovery, but some of the plasma that does make its way into the Earth's magnetic field, and there's really two sources. I've so far only been talking about the solar wind, bringing in these ionized particles from the sun, but also the Earth's atmosphere, the upper atmosphere, the particles can become ionized and then go outwards. And so there's a thing called the polar plasma fountain, I think it's called. Actually, my roommate who lives in Nashville, that was what his PhD thesis was about. So that's more his thing. But you can actually have some particles of Earth origin that can also make it into this innermost field in the Van Allen belts. And one of the ways they can tell the difference is by trying to determine which ions they are. So if you just call it all, protons, then you're really missing a bigger picture, because what if you have some oxygen ions? What if you have, nitrogen ions? And so that can actually tell us, because there's a lot more of those, of course, in the Earth's atmosphere than there is in the solar wind. The solar wind is going to be more like the sun's composition, mostly hydrogen and helium, and a little bit of everything else. Whereas particles coming from the Earth have a much stronger, amounts, but much larger amounts of oxygen that become ionized to get in there. So by looking at the sort of hydrogen to oxygen ratios, you can kind of figure out or start to figure out how much of it was from the Earth and how much of it came from the sun. And of course, because of the solar wind flow, the supersonic flow past the Earth's magnetic field, we have the magnetotail. So the Earth's magnetic field gets stretched out to tens of Earth radii, some cases hundreds of Earth radii behind the Earth. It's far enough that actually when the moon is near full moon, it's actually in the magnetotail. Whereas most of the rest of the moon's orbit is far enough away from the Earth that it's going to be typically be in the in the solar wind. Occasionally in the plasma sheet, or in the magnetopause area or the magnetosheath, but mostly the moon's going to spend most of its orbit just in the solar wind. And of course, the moon's interaction with the solar wind is interesting in itself because it's not a magnetized body. And so the solar wind literally just smacks into it with no warning, because there is no shock wave, there is no mechanism to transmit, because there's no magnetic field to transmit that information that the moon exists. And so the solar wind just smacks into it. But there is part of its orbit when it's near its full moon that actually does go through the tail. Right along the equator, you can see that there's a really sharp kink in the magnetic field. In order to get a really sharp change in magnetic field, you need a current. And so we have a current called the plasma sheet, which is very energetic particles flowing in this sort of equatorial region of the tail. And that's actually most of the source of the particles that come down along the field lines and cause the aurora. You might think that the stuff coming in from the cusp would cause aurora, and there is an auroral spot caused by the cusp, but it's on the day side because it's towards the sun, and so that's not really what you see when you're seeing the aurora at night. When you see the aurora at night, you're seeing these hydrogen particles that are being dumped into the atmosphere from the tail, and that can be sort of precipitated by this large amount of coronal mass ejection or whatever from the sun that makes the whole front end of the magnetic field compress, and then the things go crazy in the tail, and it's a bunch of material dumped from the night side onto the auroral regions. And as you can see, that as you go closer and closer in towards the Earth, those field lines are connecting to the Earth's atmosphere more and more equatorially. And so the more closer to the Earth the stuff gets on the night side before it flows along the field lines to the atmosphere, the further south you get the aurora. And so it only takes a really highly energetic event to get that close to the Earth along the equatorial plasma sheet before it follows those field lines into the atmosphere and it gets lower and lower, so you can see it in Nashville, but apparently not in Abilene. Okay, not that I'm bitter. And then this is sort of the putting it all together, right? So you see the inner magnetic field and the radiation belts. You see the plasma sheet, and then the magnetopause, sheath, the unimpeded solar wind coming in from the sort of bottom left, and so this is sort of a standard type cutaway picture of all the different regions all put together. Okay, so now moving on to our applications. It's all well and good, right? But how does this affect us, whether we're in Abilene or we're in Nashville? What does this really, other than maybe occasionally get to see the Northern Lights, why is this really important? And so we're going to start talking about why it's important by looking at our nearest neighbor planets, Venus and Mars. And so we start with Venus. We see that we have a very slow rotation, which you may already knew that Venus rotates on its axis very slowly. And so there is no sort of differential stirring up motion of the inner core, the outer liquid core, assuming it even has an outer liquid core. I'm not sure if we even know that one way or the other. But even if it has a liquid outer core, there's not enough rotation to generate a magnetic field. So Venus lacks a magnetic field, but it has an atmosphere. And so what that means is that, as you can see here, the solar wind interacts directly with the atmosphere rather than the bow shock being like 10 and 12 Earth radii away. Venus is about the same size as the Earth. It's just like one radius above the surface, which means that you have a lot more direct interaction between the magnetic sheath, this shocked subsonic plasma, and the upper atmosphere. And the main consequence of that is that Venus has lost most of its hydrogen. Right? Why hydrogen? Because it's the lightest element. So if it gets loose, it's going to go up high in the atmosphere. It's going to become ionized. It's going to see that solar wind magnetic field, and it's going to be ripped away from the planet. Whereas the Earth has managed to hold on to most of its hydrogen, and so most of our oxygen has combined with hydrogen to form H2O, right? Which is our oceans. And yeah, it's weird, but planetary scientists consider the oceans to be part of the Earth's atmosphere because it's just easier when you're bookkeeping all the different elements to just treat liquids and gases as all atmosphere, or just call it all volatiles and be done with it. But in the case of Venus, since it's lost so much hydrogen, most of that oxygen has combined with carbon, and so we have a heavily carbon dioxide atmosphere, which of course gives us a runaway greenhouse effect and hellish conditions on the surface. But if you think about just the pressure on the surface of Venus, which of course is really, really high, it's actually pretty equivalent to the surface at the bottom of the ocean. So again, it's just think about the oceans as being sort of part of our atmosphere, then being at the bottom of the atmosphere on Venus is equivalent to being at the bottom of the atmosphere on the Earth if you're at the bottom of the ocean. And in that case, the pressures are pretty similar. And one thing I like to tell my astronomy students to blow their minds is nitrogen is like about 1 or 2% of the atmosphere of Venus, where it's like what 78% of our atmosphere, but it's the exact, well, not exact, but it's pretty much the same amount of nitrogen. It's just that they're, I say they're like there's people on Venus, right? But Venus's atmosphere has so much carbon dioxide that the nitrogen, which is the same amount we have, is just a very small sliver of their atmosphere, whereas it's the majority of the Earth's atmosphere. So I think that's cool. And then our other example, of course, is Mars, where we have the same problem, but for the opposite reason. So Mars rotates rapidly. It's only slightly different from the Earth. It's like 24 and a half hours, roughly. We call that as a sol. If you ever watch like The Martian, they talk about Martian days as sols. So that's not the problem. The rotation is not the problem. The problem in the case of Mars is it's way smaller. It's only about half the size of the Earth and Venus, and it's farther from the sun. And so its core has cooled to the point that it doesn't have a liquid layer. And so therefore, it only has very small pockets of magnetic field, which are basically remnants of global magnetic field that it would have had. So you have basically parts of the surface that are still magnetized from a time when there was a global magnetic field on Mars, but it's no longer. And so here we can see, again, the interplanetary magnetic field and the solar wind interacting basically directly with the outer atmosphere of Mars, stripping away, in this case, much of its atmosphere, the not just the hydrogen, but all of the atmosphere has been largely lost. There's very only a very thin atmosphere left, and so Mars is also dead and inhospitable because it lacked that magnetic field to help it hold on to its atmosphere. If, of course, looking at the sun, of course, we know that the sun is very dynamic, as we saw a few days ago, and it's constantly giving off the solar wind, but it's very, very dynamic. That is, the density, the speed, the magnetic strength and polarity, all these things change pretty regularly and rapidly with the solar wind. But then, in addition to that variation, you sometimes have these huge blobs of material that will detach from the corona of the sun and flow out into the solar wind, called coronal mass ejections. And these are the kind of things where our human scales really don't work, because you can talk about these things as having masses of billions of tons of plasma, and being the size of 100 Earths or whatever. And it's crazy, but even over the entire 10 billion year lifespan of the sun, it's not going to amount to any significant mass loss. The sun is that heavy. It's like what, 10 to the two times 10 to the 30 kilograms or something. It's just insanely massive body. So that billions of tons is like nothing. You don't even notice it, even over spread over billions of years. So it's crazy that it's so much mass to us and yet so little mass to the sun. Of course, in general, the study of the um, the dynamics and the interactions between the varying plasma from the sun and the geomagnetic field is what we call space weather, right? So if you were looking at the space weather report a few nights ago, then you would have known that there was a major geomagnetic substorm and they were expecting really big auroras. In fact, I didn't see them until after I started seeing the pictures, but some of my advisors and colleagues who keep up with that sort of thing more closely than I do were posting about it on Facebook even before pictures started showing up. So it was expected. It wasn't a surprise to scientists, but of course most people, including myself, because I was busy with final exams at the time, most people weren't watching the daily space weather report. Um, some of the sort of everyday problems that can arise from these is you can cause induced currents that can cause blackouts. You can have induced currents within satellites. They can cause shorts and damage of the satellite. And so basically, you know, bad things to our technology. A really, really bad uh, event like this, the one that 150 years ago or whatever was causing telegraph lines to catch on fire from the induced currents. Um, if that sort of thing happened today and we weren't ready for it and didn't prepare by, say, shutting down systems and turning off power grids, it could fry the global power grid. And so I sometimes tell people, as a magnetospheric physicist, there's different things that keep me up at night than regular people. I still have the regular people things, but I also think, if just the wrong solar storm hits us in just the wrong way and our grid operators aren't prepared, you could take out the global power grid for weeks, months. Can you imagine what that would do to our economy, to our civilization, if suddenly there was no power for a month? It's pretty scary to think about. But um, I hope and certainly believe that power grid operators are very well aware of this danger and that they have plans in place. So that hopefully that would never come to pass. But that's sort of my nightmare scenario as a space weather person. Okay, so we mentioned earlier the cosmic rays, and you can see that these are coming in super high energy. They come from distant parts of the galaxy and even beyond the galaxy. They can be accelerated by supernovas and other, crazy things going on in deep space. And a lot of them don't make it to us because they're deflected by the Earth's magnetic field. And as you can see, even in this picture, a few of the little arrows do make it to the surface. So our second line of defense is the Earth's atmosphere. So they hit and scatter and break into a bunch of subatomic particles, and we get a rain of subatomic particles whenever one makes it to the atmosphere. Most of them don't even make it to the atmosphere. So we have sort of two lines of defense in that case. And then, of course, trying to study this, you can study it from the ground. You can take pictures. You can measure the Earth's magnetic field at different Earthbound stations, especially at high latitudes. But to really understand what's going on, you obviously have to go there. In fact, when I was a grad student, people would ask, "What's the difference between space physics and astronomy?" And our standard answer was, if you go there with a satellite, it's space physics. If you look at it through a telescope, it's astronomy. Of course, there's some crossover, but for the most part, that's how we sort of broke things down at the time. And so this is a mission I've mentioned before called Cluster. It's, you can see four identical spacecraft that fly in formation. And this is really helpful because the things that are happening around you are so big and move so fast. Let's say you go from one region to another. Well, is that because you were moving through that one region to another, or did that boundary pass over you? Which with one satellite, you can't tell the difference. But with four, you can distinguish. Did we pass through a stationary boundary, or were we basically stationary while a boundary passed over us? And so that's a really important thing. That most of the newer missions, this one's launched in the late 90s, and most of the missions since then have been multi satellite missions. One you hear about these days a lot is MMS, multi Magnetospheric multi satellite mission. I don't remember. Uh, anyway, but Magnetospheric multi scale. That's what it is. Magnetospheric multi scale, which is an ongoing. I think cluster is still active in an extended phase, but I don't really work with them anymore. It's primarily led by ESA. In fact, the very first cluster was actually destroyed. They had it was the first launch of the Ariane 5, which is now retired, and because of a software glitch left over from the Ariane 4 days, the spacecraft overran some parameter and suddenly thought it was going in the opposite direction and self-destructed. And so they lost all four cluster satellites on the first Ariane 5 mission. And then they later launched them 2 and 2 on a different, I can't remember what booster, but they launched them after they built them all over again. They launched them 2 and 2 because they weren't. And then this is from my own work that I mentioned earlier, where you have the cluster mission up in the high altitude cusp, and then you have the MSP. You can see DMSP 13 is labeled there in the low altitude region, and trying to connect those. It's trying to predict when they're going to be on the same magnetic field line, because that's what matters, right? Being at the same latitude, longitude, that doesn't matter. What matters is that we're on the same field line. So you had to use a magnetic field model and the parameters of spacecraft trajectories to figure out when they were on the same field line and try to correlate their data. So that's mostly what I did when I was at Goddard. And then this is showing what that passage through the cusp at low altitude would look like. This is some older data. In fact, this may be, I don't have my notes here, but I think this is possibly the very first detection of the cusp that was Heckel and Winningham in 1973, maybe. And so you can see, well, I don't know if I can y'all see my arrow? So does my arrow show up on y'all's end? Moving around? Yeah. Okay, so you can see this sort of hump where it's got higher energy on the ends and low energy in the middle, and this is sort of the characteristic. And here you can see it, and here you can see it, sort of characteristic of passing through the low altitudes cusps. And so that's the very earliest detection. And then here is the Medusa instrument on Astro 2, which is my instrument. I built and calibrated Medusa. I didn't design it. Another grad student did that, but I built and calibrated it, and so that's kind of my baby. And so you can see here the same kind of thing. We can see here especially here in this in the ions. You can see that sort of uh, high on the ends and lower in the middle. And you can see it down here in the antiparallel ions going like that. So so that sort of connects, I guess, my predecessors to my own work. And then to wrap things up, uh, the Earth wouldn't be habitable most likely if we didn't have a global magnetic field. So when people ask why is what you do important, I say, well, it's a good thing we have a magnetic field, or we wouldn't be here. And of course, understanding that's something that important is also a big deal. All right, so that is it for my slideshow. Looks like I have what, about 45 minutes from the time we started. So if anybody has any questions, let me see if I can remember how to stop sharing my slideshow. Okay, there we go. So I guess if anybody has any questions, we can go to that.
Well, thank
Do,
you,
do
Wayne.
we have it? First of all, thank you very much for the presentation. It was awesome.
Oh, great, thanks.
The shift, the flip in polarity, do we have any understanding of the mechanics behind that? Is it a slow migration or how does it work?
Um, well, it's slow probably by human standards. It's very, very rapid by geological time. And so, we look at the geologic record and we look at, say, the alternating positive negative polarity of the ocean floor. It happens almost instantaneously geologically. But instantaneously on geologic time might be tens of years, it might be hundreds of years. That's actually a big question. Of course, because the magnetic poles are currently moving and the magnetic strength is changing and weakening, there is some speculation that we may be getting close to a pole flip. Unfortunately, the physics of the dynamo of that generates the magnetic field in the Earth's core is extremely complicated physics. And so, yes, we have built models, and yes, we can kind of sort of model and predict how a pole flip works. But until we experience one firsthand, I don't think we're going to know exactly what's going to happen. And of course, that's actually a big concern, again, for our technology. We know that the Earth and life on Earth has experienced and been fine through many pole flips. It's never caused an extinction that we've been able to correlate it to or anything like that. But what's a lot more vulnerable than life on Earth is our technology, right? So just the same way that a really big geomagnetic storm could, wreak havoc with our power grids, if we say had a 50-year period where there was a very weak magnetic field and we were much more affected by just the solar wind in general and by any sort of storms from the sun, then we would have to basically rethink our power grid. We would have to, hopefully it would happen slow enough that we could adapt. Obviously, in the disaster movies, it always happens over a weekend because you want the things to keep snapping along with your movie. But in reality, we'll probably have enough notice because it'll happen slow enough on our human scales that we'll say, oh, the field is getting weaker, and so we need to start thinking about new ways to protect our grid, and so there may be a time where our power grid looks very different than it does today, 50, 100 years from now, if we're going through a period of weakened field due to a pole shift. But we really just don't know if it, when it comes to deciding is it going to be 1 year or 10 years or 100 years, it's still really hard to predict that part.
That's interesting. So that actually kind of gets to one of my questions I had. You mentioned that people understand when these things are going to happen. You mentioned hopefully the people running the power grid know a little bit about this stuff. What exactly they do? They just shut stuff off? Like,
It depends, but one of the things that they can do is actually shut things down. I think that's a relatively extreme reaction. If there's, like, for example, in Canada and in any place of northern latitudes where this sort of thing is a lot more common, and Canada has had blackouts due to geomagnetic storms, so they do have experience, and it does happen. And so they have a lot more experience with how to, detect when the induced currents are starting to ramp up and be able to sort of shunt that extra power someplace, or do something with it, or shut things down. And I haven't ever studied exactly how they mitigate it. But like I said, a worst case scenario is you blow out some of these big transformers. We're not talking about the transformer that's behind your house that steps it from a few hundred or a few thousand volts down to the 120 that you get to your house. But of course, when you're going from the big high tension lines coming from the power station down to the sort of residential power lines, you've got these huge transformers. Usually you see them because they've got a big chain link fence around them. You got these big things with the big, the what we call the big insulators, right, sticking out everywhere with the serrated ceramic. Um, those things can cost millions of dollars and take months to build. And so one of the things that I know a lot of people in the space weather community have been telling that the power grids that they need to do better is to have more spares of those things. Because if you blow out one, okay, fine. But if you blow out 100, all over the grid, all over the United States, like, how are you going to recover from that? Because you need power to build the new ones. And if you've taken out the whole grid because you've blown out most of these high voltage transformers, that's the kind of thing that can really just decimate the grid. And that leads to the nightmare scenario of, just imagine, a month with no electricity. What would that even look like? Will the United States even exist after a month of no electricity?
Stone
Right?
Age.
Yeah, exactly. It's like, you read all these books about some, either magic or some other reason why poof, all the technology goes away. You don't need magic. All you need is just the power grid to go down for a month, and there you go. We're back in the Stone Age. So, like I said, that's the kind of thing that keeps me up at night, but not too often because, like I said, I do have faith that I'm not the only one that knows this is the problem, and that a lot of really smart people have probably been working on the problem. But so even though I don't know how prepared they are, fingers crossed. And of course, my confidence was a bit shaken a couple of years ago. I don't know how bad it was in Tennessee, but you probably heard about the whole Texas power grid going down for like a week. We had this big ice storm, and actually, my house had power for most of that. We did lose water because the city lost power to their water pumps, and then things started freezing up and stuff. And so we actually went several days with no water, but we never lost electricity because we are on the same substation as an emergency room, and so they got priority. But people just a few blocks away from us went 3 or 4 days without electricity, and it was also, like 20 degrees outside, or 0 degrees outside, and it was it was bad. There was a lot of hardship, and there was people that died. Um, I don't know if they ever heard final count, but I think it was in the hundreds statewide of people that froze to death.
Yeah.
Just the guy just down the road from us in Buffalo Gap went out to check his mail, tripped and fell. Older guy, and of course in that case it was very extreme because he was outside, and like they found him just froze to death in his front yard.
Hmm.
So
That's wild.
yeah, it's crazy. So
Any other questions before I throw another one at him? I just
I was
like
ready.
all sorts of random questions. So, you had those images of the way that the magnetic field kind of flows around the Earth and stuff like that, and you essentially had the Earth straight up and down, but everything tilts, right? And so, how does that impact like the possibilities of seeing things like auroras and stuff like that, right? Like, do you have a better chance in the winter, in the summer, kind of, you know what I'm saying? Like with the tilt.
Right. Well, the thing is that the annual tilt isn't actually the biggest thing because the Earth's geographic axis and the magnetic axis are off by, I forgot the exact, 30 degrees or something. And so on a daily basis, the magnetic field is doing this, right? And so I don't know that there's a seasonal difference other than just, you know obviously in the winter it's easier because it's nighttime longer, and you can really only see aurora in the nighttime because the sunlight just overwhelms it. In fact, who was it? Was it Theo that was talking about how as at sunset you started to see something weird, right? So during the daytime, you just can't see it, and so even though that material from the magnetospheric cusps is basically coming down and putting a spot on the Earth's atmosphere all day every day at the right latitudes, nobody ever sees it because it's always in the daytime. Except maybe some rare occasions like when it's, northern hemisphere winter, and it's the part of that part of the day where the magnetic field, if things get far enough over, then maybe it would hit in the night. You do get the whole midnight sun thing going, in the Arctic, where you have, never gets dark in the summer and it never gets bright in the winter. In fact, the time I mentioned earlier, I don't know if you were on yet. We were talking about seeing auroras, and in '97, I went and spent a month in Kiruna, Sweden, when I was working on that Medusa instrument. That's where we did the calibration, and it's 100 kilometers above the Arctic Circle, and it got dark in October. It got dark at 3 o'clock in the afternoon. It was crazy, and so I would go out, after work, I would go outside and put my big coat on. It was already snow on the ground in October, and I would just lay out there and watch the auroras. And there were several times, so I was there for a month, and there's several times where we had some decent auroras. It's not anything you'd be able to see, from our latitudes, but they're right under it all the time. In fact, on the roof of their building, they have an all-sky camera that is just an auroral camera, and it just takes pictures of the aurora all night, every night, because it's so common there. And I mean, there's a reason why there's a magnetospheric physics lab, in the Arctic Circle, because it's just you're right there under it. So that was pretty awesome. I did get to make a couple more trips there, but they were both in the summer. And so I didn't get to see any more aurora, but I did get to experience the midnight sun, where it never got dark. And that would mess with you too, as a Texas boy. And I remember, because they actually had some like trailer houses that were right next to the institute where I was staying. And so, I didn't have anything else to do. That meant that my TV got 3 channels and 2 of them were in Swedish. And so I would, after dinner, I would sometimes go back to the lab, because I was just, 20 feet away from it. And I would do some more calibration work. And I remember one night I was like, man, it must be like 9 o'clock. I've been here so long. I look at my watch, it was 11:30. I had no idea, but there was still light coming. There was windows in the lab. There was still sunlight coming through the lab windows, and it just blew my mind that it was still daylight. And it was 11:30 at night. So I'm like, yeah, I should probably do
that. I got one more question for you before I let you go. Does anybody else have any questions? Yeah, yeah.
Do you know what the parameter BZ is?
Do you know what the parameter BZ is?
Yeah, BZ is so when you have the magnetic field, they split up the magnetic field direction into an XYZ. And so BZ is just the Z component of the field. Typically, when you're talking about BZ, you mean the BZ of the solar wind, because whether if Z is up, then you get field lines this way. If the Z is down, you get field lines this way. And so the interconnection that I was talking about, that depends heavily on the direction of BZ, whether your solar wind magnetic field is up or down. And so that's why you hear people talking about BZ. I assume, of course, I don't know what context you're hearing it from, but that's what I would assume is the case.
Radio.
The radio, yeah. So if they're talking about BZ and with regards to the solar wind and the aurora, they're probably talking about that. They're probably talking about the Z component of the interplanetary magnetic field.
You know what K index is also?
I can't explain the details of the K index, but I think it's based on a ground-based measurement. And so they're looking at the changes of the Earth's magnetic field. So it can see things like how the field gets compressed when the solar wind is hitting it, when there's a big blob of plasma hitting the solar wind. So the K index, KP index, it's a ground-based measurement, and it tells you how active the field is. But I don't remember the details of how it's calculated.
Would you have an opinion whether minus BZ is a better predictor than K of storms? Just not.
Yeah, not really.
Right here.
Yeah, sure.
Any other questions real quick? Yeah, go ahead.
Represent the life, right? And so we're in this golden age of discovering exoplanets. So the question becomes, I don't know if we can detect it that far out, but have we discovered exoplanets that have been moving?
Did you catch that?
No, I couldn't hear it. Sorry.
Yeah, so basically, how important the magnetosphere is for life on Earth. Do we have the capabilities of detecting the magnetosphere on other planets? And
Oh,
can
that's
you,
a good question.
what is that?
Um, I think the answer is probably no, because magnetic fields they tend to trap the particles, and so we don't have a lot of things flying interplanetary or interstellar distances that sort of let us know it's there. I don't know how we would directly see it. For example, we didn't even know that Uranus and Neptune had global magnetic fields until Voyager got there. So Voyager 2 did their flybys in the what late 70s or the 80s when they did the Voyager flybys. So I assume that even with modern technology, I don't know of any way we would be able to detect the global magnetic field of an extrasolar planet. I think if we're going to be looking for life on these exoplanets, I think we're much better off looking for chemical biomarkers in the atmosphere, which is what they do because they're smart. The people that do that sort of thing, which is I don't work with that directly, but of course I talk about it in my intro round class.
Yeah, so
That's a good question.
yeah, one last follow up on that. So thinking about us trying to colonize other places like the moon and Mars, like how are you gonna? I guess how are they planning on protecting from the harsh?
Yeah, that's a good question. In fact, once you're on the surface, you can just go underground, and I've seen both science fiction and like real science planned Mars and moon colonies where they talk about going underground and if not digging a hole underground, you build your habitat and then you pile up dirt over it. You know, um, but of course, with Mars, it's got these lava tubes, basically. Actually, the moon also, and Mars both have lava tubes, just like you have in Hawaii. And so there's places where the top of the lava tube has been broken, and you can see down into it. You can see that there's actually a cavity. And there was, I think it was a mini series. I can't remember what channel it was on. A mini series may have been called Mars, where they actually built a habitat down in a lava tube on Mars. So that is a real idea. The bigger problem is actually when you're in interplanetary space in your spacecraft, because transit times to Mars are months. Even if you do an efficient home and transfer orbit, you're talking months of transit time to get from Earth to Mars, and you need a way to protect your astronauts then. And the two main things I've seen is either have a bunch of like water tanks or fuel tanks or something around your habitable area to use that mass to in the same way they use the dirt to stop the particles, or you in some cases, assuming you have a spacecraft design that's got plenty of energy, plenty of excess power, you could literally generate your own little mini magnetosphere. And I've seen plans for that. But the problem is, you basically have to have a nuclear powered spacecraft, which I mean, technically we could do it legally. It's a little bit more iffy. It's kind of a hot potato to put a nuclear power plant on a rocket and launch it. So politically it'd probably be impossible, but technically, you'd probably need a nuclear powered, or some way to generate a whole lot of energy to be able to actively generate, just from having either superconductors or just regular wires, and generate an active magnetic field, like basically an electromagnet. Um, that would be hard technically and even harder politically, but that's probably the best way to do it is just take your magnetosphere with you. And of course, there's also ideas about generating magnetic field on the ground. Although in the case of Mars, as I mentioned during my talk, there are pockets of localized permanent magnets, and it generates a little mini magnetic umbrella over that little bit of ground. Um, One of my colleagues at San Antonio, he worked on the Mars Express mission, which is a European mission. San Antonio built one of the instruments for Mars Express, and that's one of the things they were looking at is flying low altitude to the point. Oh, my wife's calling my office. I guess she's calling my office. I'll call it back. We're almost done. So uh, basically, I forgot what I was talking about. What was it? We're talking about generating the Mars Express mission would fly low enough to the surface, they could actually fly into these pockets of magnetic field and look at how the solar wind interacts differently with those magnetized regions of the surface rather than the unmagnetized regions of Mars. And so I don't know that we know for sure if that would be strong enough to work, but it might be a place where, get Elon Musk on the phone. We might want to put our Mars colony inside one of those natural magnetic bubbles on the surface. So that could also be a way to get around that problem.
So using the tinfoil hat probably isn't going to protect our astronauts.
Yeah, tinfoil hats won't do too much.
All right, good deal. Well, Wayne, thank you so much. Let's give Wayne a round of applause. All right, well, we'll go ahead and let you go. Thank you so much. I really appreciate you giving us a talk today. It was really cool.
Yeah, this was a lot of fun. Feel free to contact me if you guys have any follow-up questions later. Tom's got my email, so you can send those to me.
Yeah, I have a whole list of questions, so I'm going to be bugging you.
Okay, but you can send those to me later. Right now, I'm going to get off and call my wife back.
Yeah. All right. Thank you, Wayne.
All right. Thanks. Bye.
All right. So let's see. So I'm going to go ahead and get mine set up real quick. Screen. Here it is. All right. Can you guys see the slide presentation? Yeah. All right. I see a head nod from Theo. So we're gonna go on that. All right. All right. Thank you everybody for hanging out, and I know we're running a little bit late because of the technical difficulties and stuff like that, but again, thank you. Hopefully be able to blow through today's talk. Today is the member meeting for the month of May 2024. We had some cool things happen over the last couple of days. All right, we had the Northern Lights come in. Right, this is my image from Bellevue. We have this big beautiful sun coming through here, right? I was actually looking up the Carrington event when somebody posted about it in our Google group. It was pretty interesting seeing those side-by-side comparisons of the solar spots that we had coming through there. So it was actually really cool to see those kind of things. We'll talk more about that in a little bit. All right, so we'll go ahead and get things started. Hopefully everybody had a chance to take a look at the member meeting, the minutes from the member meeting, as well as the board meeting in this month's magazine. Anybody have any questions about the previous minutes? We didn't get a chance to have a board meeting. We didn't have a quorum, so we'll pick up some more business this upcoming month. So, but were there any questions from what we read? All right. Theo, or actually, Keith, you got a member report?
Yeah, we are up to 191 members.
Awesome.
We've had a pretty steady stream of people, about 1 or 2 a week.
Good deal.
Doing well.
Yeah. Theo, you got a treasurer's report for us?
Yep, not much change from last month. We still have a bank balance of $9,396.32. Pretty much what we spent money for last month was the Zoom account, and then $150 for our MTSEF prizes. Upcoming, we get to pay for our PO box for another year, which I need to go visit, and then we'll be re-upping our membership in the Astronomical League as well. But And we have $227.82 in PayPal because, yeah, we keep getting those new members. So that's very good. I did sell a poster in May. It seems like whenever I go out of town, somebody orders a poster. So I guess I should stay out more.
Get you traveling.
Yeah. So it's all good.
Awesome. All right, thank you for that. So any new members here today? Seems we're getting a few. Any visitors?
Hey, I'm a new member,
Okay.
Danny Baggett.
Nice to meet you, Danny. I see you're here in Nashville.
Yes.
Awesome.
Yeah, actually, I'm in Hendersonville. I just put that
We'll
up.
accept you still.
But yeah.
Oh, hey, Danny, I'm almost your neighbor. I'm up in Goodlettsville.
Oh, all right. Oh, good to meet you.
Small little world. Well, welcome everybody. As we mentioned, this is a member meeting, but we are welcoming the public as to this event as well. One of the perks of being a member is we have loaner equipment that you can use to check out future potential telescope purchases, or if you're just wanting to see what all you can see from one of these big beautiful Dobbs or some Newtonia, or just checking out different kinds of scopes to see what's out there, feel free to reach out to us. We have a variety available. Our list is up on Google Groups. My semester just ended last week, and it is on the docket to update our list to make sure that we have everything available to you guys. I'm going through and checking eyepieces and making sure everything is functional and everything before we start getting things sent back out to you guys. But if you do have a scope that you are borrowing from us, let us know how it's going. Feel free to ask questions, tell us what you're seeing, what you're not seeing, what you wish you could see. And we may be able to help with that. Also, we have star parties and things like that. If you're wanting to interact with the public and share your love of the night sky, feel free to grab one of these loaner scopes and come on out with us and take a look at the sky with the public. It's actually really enriching to see people go, wow, this is amazing. So it's pretty cool. Upcoming meetings, as mentioned before, this is our first year at Dyer, and with that comes some scheduling hiccups. Next month's meeting is no longer the third Wednesday of the month. It's actually the fourth Wednesday, and I'll make one more announcement as we end. So next month's meeting is June 26th, because the 19th is the Juneteenth holiday. So make sure you mark that on your calendar. I'm sure I'll send a notification out the week before the third Wednesday, and then the day of that Wednesday, to make sure people know that we're meeting on the 26th. So you'll hear some more from me. And then the next month, July, Dyer's having a camp week, and so we're pushed a week later there too. So it shouldn't be an issue. We have some cool speakers lined up for that. Next month we have a talk on starquakes, kind of like an earthquake but in a star. And then after that we have somebody that works for the James Webb giving a talk to us. And so we have some cool things lined up for upcoming talks. You can find us on our website, bsasnashville.com. We have a whole host of things coming up here. We do our best to maintain our calendar updated, or maintain our calendar. We have our next public star party, which is Saturday. Yep, a couple days from now, weather permitting. We have our next member meeting up here posted. So that's today. And then we have a future public star parties posted. We also have private star parties that are for the members only. And we have information and details on that through Night Sky Network. And we'll send out messages through Google Groups if we are planning on meeting there. As Theo mentioned, we do have these cool Hatch Show prints. If you've been with these for a while, you've seen me plug these every month, but they are pretty cool prints. And if you're a Hatch Show fanatic, they did build us a very cool stencil that we were the first ones that they used. So there's some historic value to that. Also on our website, we have a couple really cool links. You can get to all of our socials here, which we'll run through shortly. We also have a link to our discussion forum, which is a link to our Google group. And so if you're wanting to interact with us in an outgoing or outreach way and whatnot, and see what's going on with us behind the scenes, or any type of news and events we'll probably post on, go check us out there. And then if you're ever going to go out and view and you want to see how good the sky is going to be, we have this cool clear sky chart centered around Nashville that essentially goes through and tells us how dark the sky is. And so the lighter it is, so the white you want to stay away from. So Friday, don't plan on going. You know, do yourself a favor, just don't even waste time. In fact, it doesn't really look good through the weekend. Tonight around, I guess, midnight might be okay, a little bit before, but still wouldn't hold my breath, right? So, but it's a pretty cool indicator of how good the sky is going to be. So you can kind of plan for what you're going to see. Let's see, we just took off the website the statement about glasses for the eclipse, and I just wanted to throw in here that we are collecting used solar glasses or any glasses that you just had extra. I have some mementos, right? I'm going to keep mine from the eclipse, but I had extra, so I don't need those. And so Astronomers Without Borders is collecting them to give to places where the eclipse will happen in the next couple of years, that they won't have access to glasses, and so they're donating them there. So I'm signing up to be one of the collection sites for these glasses. And so if you have glasses that you want to donate, feel free to bring them to a meeting. I can take care of this for you. On Facebook, we're rocking and rolling. Thank you, Donna, for helping keep Facebook updated and things like that. There's some cool posts that show up. I just wanted to highlight this, the Astronomy Day, May 18th. And so that's this weekend. There's 2 astronomy days per year. And this is essentially where I think I have it on another slide. In 1973, a gentleman in California wanted to get out into the public and show people that, you know, you don't need just pure pristine skies to see stuff in the sky. So he'd set up a telescope on the side of the highway, and people would stop and he'd just show the sky, and, you know, all in the sake of outreach. So we're kind of doing that whenever we go to the star parties and create these atmospheres for the community. So that's a post on there. There's also posts of our upcoming events and things like that. All right. Also this was me. I got excited. It's like, oh my God, there's stuff going on. People check. And so I'm sure probably won't be my last spontaneous OMG post. But stuff going on in the sky. We'll often have ISS passes and things like that. So it's cool to keep track of. That's what's going on. This is on the Twitter page. This was Aurora near Jamestown, Tennessee. Theo, did you post that? Can't hear you. You're still muted.
That was off the phone. And so it was just, you know, I don't have a really up-to-date phone or whatever you call it. So that's kind of, you could see that with your eyes. I mean,
wow.
That was definitely visible. And if anybody's been to the astronomy field at Pickett, I want you to imagine it with a full to overflowing parking lot. It was just, and because everybody heard about it, the next night they did the same thing all over again.
Yeah.
We had people parked on the side of that road, which I personally wouldn't do, but you know, people were doing that. So we had a really nice group of people for about 2 hours just going, ooh, ah. It was kind of fun. So
awesome.
yeah.
Well, that's cool. So thank you for posting that on Twitter. We're not as active, but we do post things here and there. Same thing on Instagram. We have a few people helping out with the Instagram page. Like Steve, here you can find some member meetings. We need to, I know I need to get on there and start posting some images, because we're starting to see a lot of them come through the Google groups. And so we'll start getting that active again. But if you do take pictures and you want to show them off to the world, we'd be glad to put them up on our page for you and give you credit and all that good stuff, because, you know, it's an awesome hobby. It's great to share these things. So feel free to send it to us at info@bsasnashville.com or post it in the Google groups. I may reach out to a few people who've posted lately, seeing if you'd mind if we posted them on Instagram and Facebook and stuff like that. But it's a great platform for sharing images. Now, speaking of Google groups, this is our landing page for our Google group at BSAS Nashville. It is a members only group, so if you're a member and you don't have access to this, please reach out to us and we can get you into it. Here you can see we have all sorts of postings all about the Aurora, of course. Then we have ISS passes and questions that people are going out. This is, like I said, people post pictures. Here's one. Yep, there we go. Have to do this. Beautiful aurora behind a fantastic telescope. This resonated with me for some weird reason. Anybody else see that? I was immediately drawn to it. I was like, that is an amazing image. But that's really cool to see that aurora. If you ask me, I'm pretty sure Theo hit the jackpot. I don't know who she bribed or whatever to end up at Pickett for this wonderful event. There's Theo's shot. Yeah, I don't know. You lucked out on that one. Well done. Let's see. And so again, if you don't have access to the Google groups, definitely reach out to us. Theo's wasn't the only image up there. We had a whole host of them, right? Like just various shades of pink, greens, and reds all throughout the Tennessee area. So it was a really cool event, right? Like I don't know the next time we're gonna see the aurora here in Nashville. I saw somewhere online that the Icelandic nation just lost a whole bunch of tourism money because the once in a lifetime trip to Iceland to see the aurora just went out the window. So pretty cool to see all these images come through. It was really exciting. We run our group through the Night Sky Network. So if you are a member, you should hopefully be familiar with the Night Sky Network. You had to sign up for them. Through the Night Sky Network, we get discounts on astronomy and Sky and Telescope magazines. So those are pretty good publications. They also have a whole bunch of really cool information on there for simple outreach. This is the featured article, or one of them, on Night Sky's landing page, Circumpolar Constellations Part 3. And so they had Part 2 up for a while. Part 1 was earlier in the year. But circumpolar constellations are the ones that kind of stick around the sky all year round and look to rotate around the northern star. And diving into that, they have this cool image up of what you can see. We have M81 and 82, the Garnet Star through here, and then my favorite, the Cat's Eye. Not my image. That would be amazing. It's one of my favorite images of it, just because the cool shapes and colors that you can get through it. But tiny little thing if you get a chance to image it. So, but I'll definitely be attacking that. And then also, they had one of their featured articles on stargazing for beginners. And so if you don't know where to start and where to look, it's a pretty cool article on quality of sky and what to look for whenever you're trying to figure out what you're going to go after going out, like what to see. I put a screenshot of this because it shows something that's pretty near and dear to us that love the sky, essentially looking at sky quality, right? And so the further you can get away from these inner city skies and get out to more rural or even the suburban sky, the better chance you're going to see some of these features that only lend itself to really pristine skies and stuff. So like Pickett is kind of over here in this area. Nashville, we're over here. So this image just kind of shows what we're actually missing by all the lights that are going on in our neighborhood. In this article, they also had this kind of night sky map for mid-May. We look, here's our whole star, and you can see everything kind of coming around. So it gives you a good idea of which way to look to see some of these constellations up there. Also, red lights. As I was out imaging the northern lights on the Natchez Trace, no red lights. It was very blinding, but it was still pretty cool of an event. But it goes in and basically talks about saving your eyes, right? Because you want it to be as dark adapted as possible, so you can start seeing some of these things come out. Because when you first show up to a site, your eyes have to get dark adapted, so you can start collecting more light. And so red lights on your flashlights really save that. So it's just a little beginning tip for stargazing. Since the last member meeting we had, we haven't had too many events happen. I know that there was a private star party on May the 4th. I think I saw a post that somebody went out. Did anybody go out on that? They may not be here today. But we do have the private star parties. They're out on the Natchez Trace Parkway for the most part. And we have a permit for those. So I'll talk about the next one coming up. And then Friday, May 10th was our impromptu Northern Lights all across the US. I definitely used it as outreach. I went to the Natchez Trace Bridge and took some shots there, talked to people about it. And then on the Natchez Trace itself, ran into a whole bunch of people. Shared the love of the sky, showed them where north was and why we're aiming north and why we're aiming a little bit west of north and all these cool things like that. So again, just getting out and doing outreach, sharing with the public is, it's a really good feeling. So cool stuff going on. Upcoming events on the 18th, so Saturday, we're at Bowie Nature Park in Fairview. Note the time, 8:30 to 10:30. On their website, there's a flyer that says 7 p.m. I don't know if you guys have followed much about sunsets, but we don't sunset until 7:55 that day. So at 7 p.m. we aren't going to see much unless you threw out the solar scope. So keep in mind that it's 8:30 on that day. Telescopes are welcome. So if you're gonna, like I said, if you have a scope and you'd want to come out and just hang out and see how these star parties work, feel free to grab it, bring it out. Check out the outreach materials that are available on Night Sky Network. They have things to talk about that day and stuff like that. It's a really good site. On the 18th is also that Astronomy Day, right? And so it's kind of an homage to sharing the sky with others. On June 8th, we have a private star party at Water Valley Overlook. This is our darkest site that we have. We have a permit to go out there, and so that means that the sheriff's office and whatnot, the national park police won't boot us off there, and so the park rangers.
Hey, Tom.
Yep.
If anybody wants to come, they can come to my place. Less than 2 miles from the Water Valley Overlook. I have power, water, bathroom, refrigerator, microwave.
Yep. I concur on all of that. It's a fantastic place. So I'm sure if you're interested in going out, we'll post on Google Groups. And I know Ron's active on there. And so it's always good to also post on Google Groups when you're going out, because it's cool looking at this stuff with friends. So see if anybody else wants to go out there too. So thank you for that, Ron. Appreciate it. And then our next public star party after that is June 15th at Bell's Bend, 9 to 11. And again, if you're interested in bringing telescopes, we'd love to have you. At Bell's Bend, we usually get a pretty good turnout. So it's always good to have more scopes there. Coming up in the night sky, so there's some things to look at. There's a lot of things to do with the moon. As you can see, we have the full moon here, and then the moon in Saturn, moon in Mars, moon in Regulus, and then back to a full moon. It's interesting that there's nothing in between here, but we are starting to get into the Milky Way season. So there's always cool things to image there. As you've noticed in the past meetings, I always try and get on the Stellarium's web app now. So you don't need Stellarium downloaded on your computer, but you can go to their website and choose a date. And so here I went to the 31st, where you had moon and Saturn close in the sky. And so here's the moon and Saturn. Here you can get your field of view. And so if you're an imager, you can put a lens on to get whatever field of view you're after. But here you can see moon phases will be in, here's Saturn. And then as I'm getting ready to take this screenshot, all these green satellites are zipping through here. And so we're predicting it, right? Guess what these satellites are? Starlinks, right? So if you don't want Starlinks, don't go out at 4 a.m. Right. So they just started inundating the screen as I was getting ready to take images, take the screenshot. So, but this is also a really cool piece of software that helps see what's in the night sky that night. And so a little plug for Stellarium, and it's free. All right. One last thing. Again, if you have solar eclipse glasses you aren't using, feel free to bring them by. I'll collect them and then drop them off wherever they need to go. And then finally, last bump, the next meeting is the 26th. Right. So it's the fourth Wednesday of the month instead of the traditional third. Okay. And so it's because we're celebrating Juneteenth. So be sure you change it on your calendars, mark them appropriately. And like I said, I'll be probably sending you excessive emails. All right. I think that's all I got for today. Is there any questions or any unfinished business? Yeah, Steve. Yeah.
Yeah, so I was like a part of the 4-inch small tractor I have back there returning. But if anybody would like to borrow, beginner scope, it's really nice. Good. It's 4-inch tractor back to the bottom to see me. And then the second thing I just wanted to mention that the very, very nice people here at Air, so he's out there, Billy's somewhere, but they're going to open the dome up after the meeting here. And so if anybody wants to go up and see the scope, and I'm not sure if you can see the views.
I see.
Okay, so very nice of them to let.
Very cool. Well, thank you. Thank you, Steve. Any other business? All right. Well, with that, we'll go ahead and end the meeting. Thank you, everybody, for again sticking around and dealing with the technical difficulties in this wonderful world. Maybe it was a magnetic storm. Who knows? Took out my microphone. All right, everybody. Well, we'll go ahead and end there. Thank you again, and hopefully we'll see you at a star party or next. All right. Take care. Bye, Theo. Have a good day.
All right.
What they call Blue City, someplace in Africa.
Oh, this is Indy.
It's Jodhpur, Jodhpur in India, Jodhpur.
Some classes for you.
Oh, okay. Thank you so much. I appreciate it.
You're welcome. We kept a bit of a collection ourselves, just to
Yeah,
the
yeah.
keepsakes.
Yeah,
But
exactly. Yeah, exactly. I did too, because it was an amazing. Yeah, stuff to- Thank you very much. Have a great day.
Yeah.